Hello everyone, myself Ankur. I am working in DD Imaging Lab, Physics Department, IIT Roorkee. In this video, I am going to talk about our article that we have published in Electronics Letter Journal, IIT, which is titled as Optimal Frequency Combination Estimation for Accurate Ultrasound Non-Destructive Testing. In this paper, we have proposed a method to estimate the optimal frequency for a non-destructive testing system. Particularly, we have used ultrasound CT system. In this video, I am going to talk about the motivation for the paper, the methodology that we have adopted, the apparatus used to carry out the experiments, the signal processing part, the results, and finally the conclusion. Generally, for an non-destructive testing system, there are several configuration parameters that are required to set optimally to carry out an experiment. These parameters may include frequency, amplitude, energy, intensity, and the object distance between the object, emitter, and receiver. And there are several other parameters that are dependent on the type of system that we are using. In this article, we have used ultrasound CT system. For an ultrasound resonance frequency and amplitude, the parameters are also include pulse width, rise time, and fall time. That also affect the shape of the ultrasound pulse that is being produced by the ultrasound transducer. The value of these parameters also depend on the object that is being scanned and also depend on the desired resolution. For an ultrasound transducer, we can also take our measurement several number of times in order to minimize the error. In this article, we have tested the center limit theorem to optimally set frequency, and the optimal instance has been also set by the application of center limit theorem. In this paper, we have solved a sparse data problem with 18 translation and 18 rotation. The rotations are taken at a 20-degree interval, and the problem is modeled assuming linear propagation of ultrasound waves. We have taken 8 frequency candidates, which are ranging from 500 kHz to 20 MHz, and a setup has been developed to carry out the experiment. The LabVIEW codes are written to control the platform, which is used to linearly translate the object and to rotate the object automatically, and also to save the data to the user system. Other than this, the signal processing codes are written to extract the meaningful data, as we know that the ultrasound signal consists of a lot of meaningless data that do not contribute to the actual information that we are required to extract. And finally, the center limit theorem has been applied to find the optimal parameters such as frequency, and also select the optimal instance out of a number of instances. And the outcome of the center limit theorem is verified by comparing the result with the error in recovery. Error in recovery basically means the reconstruction of the object that is being scanned. The quantifying parameter is root mean square error, RMSE. The apparatus that we have used consists of air coupled ultrasound transducers and a wave generator that is required to trigger the ultrasound transducer. digital scope that acquire the signal, and also do the analog to digital conversion, and it also saves the data to the user system. A control level platform that translates which is shown in the figure. It translates linearly and also rotates. The data is being taken at each translation and each rotation, and it also includes a data processing system. The working video of the apparatus is provided in the description of the video. The acquired signal look like this. We have taken 40 wave packets that are these 40 packets are represented here in the figure 1. We have marked 9 wave packets out of the 40 wave packet, and we have marked 10 peaks in each wave packet and 10 troughs. The peaks are marked with a red circle and troughs are marked with black square. And in the third figure, we have shown a single wave packet in which the peaks and troughs are marked with red circle and black square. Other than this, the peak with the maximum amplitude and the trough with maximum amplitude are marked with green triangle. The difference between the maximum peak amplitude and the maximum trough amplitude represent the projection data corresponding to the rotation and translation, and this projection data is used to reconstruct the final profile of the object. This data corresponds to just one file, which corresponds to one translation and one rotation. The first step includes the extraction of the optimal instance. Once we acquired the data, as there are 40 instances or wave packets as shown in figure A. In this figure B, we have shown 9 instances out of 40, and in figure C, we have shown a single wave packet, and in figure D, we have done a comparative analysis of 2 wave packets. Here we have plotted the amplitude corresponding to the 9th wave packet and the 23rd wave packet. The amplitude are these are the amplitude of the 10 peaks and corresponding to the 9th wave packet, and which are plotted with green, which are plotted with blue line, and green line represent the peaks for a 23rd wave packet. And in the figure E, a pulse distribution has been plotted, which also we can also see the f-dilution corresponding to the each wave packet, and from that we can see that the f-dilution corresponding to the 9th wave packet have a smaller value that represents the better fit to the Gaussian distribution. And in figure F, we have plotted the distance between peak to mean value dm and f-dilution for all 40 instances. And here we can see that out of these 40 instances, 9 instances have a minimum f-dilution, and the 20th instance have a maximum f-dilution value. So basically we have selected 9th instance based on central limit theorem out of these 40 instances. This analysis has been carried out for each file having the data, and each file corresponds to just one translation and one rotation. If we have done an experiment for 18 translation and 18 rotation, so total number of files are 324, and as we have we have got finally the 8 experimental data, which out of which each consists of 324 files. The similar analysis has been carried out to set frequency. Here we have plotted the data corresponding to the frequency corresponding to the each frequency, and here we can see that the frequency corresponding to the 500 kHz gives us the least absolute, and then we have the second best absolute value from frequency at 1 MHz, then 5 MHz, then 1.5 MHz, and so on. So as a CLT output, the 500 kHz frequency should give us the best reconstruction. The output of CLT theorem has been verified by carrying out the R root mean square analysis in reconstruction. Here in figure A, we have plotted the root mean square for reconstruction, for a simulation, for optimal instance value, and for optimal frequency instance. The object consists of iron and that is being scanned to carry out the analysis consists of iron at other outer periphery, the aluminum at inner periphery. The diameter of the combined object is 2.55 cm, and the aluminum part have a diameter of 1 cm, and the object height is 3.1 cm. While carrying out the experiment, the beam is focused at a height of nearly 1.8 cm of the specimen. In the figure A, the optimal instance value represents the reconstruction for the RMSE in reconstruction for each frequency when the optimal instance out of multiple instances has been selected, and the optimal frequency instance represents the RMSE in reconstruction when optimal frequency has been selected out of multiple frequency, and also the optimal instance has been selected out of multiple instances. Here we can say that the optimal frequency instance have a minimum RMSE value, and for optimal instance value, the RMSE is given by the minimum RMSE is given by 0.5 MHz, and then 1.5 MHz, then 2 MHz, then 5 MHz, and so on. These are correlation in RMSE and the center limit theorem output has verified the hypothesis that the optimal frequency can be set by applying the center limit theorem. In figure B, the image of CSIR phantom is shown. In figure C, we have shown the simulated reconstruction, and in figure D, we have shown the optimal instance value corresponding to the one frequency of 1 MHz. In figure E, we have shown the reconstruction corresponding to the optimal frequency instance, or it has been also called the multispectral data, as it corresponds to the best frequency which corresponds to each translation and each rotation, which is taken at different angles. The result concludes that the mean parameter frequency set at the emitter end can be obtained by the center limit theorem. For a heterogeneous object, this optimal frequency value is found to be scanning angle dependent, which is presented by the optimal frequency instance. As the object consists of two material, namely iron and aluminum, the optimal instance value is a combination of several frequencies. And if we have a material if we have an object or having several materials, the scaling frequency will be dependent on several frequency values, on the combination of several frequency values. This exercise confirms the hypothesis and verifies that one can design the optimal configuration of ultrasound CT parameters, which are obtained by the center limit theorem. The limitation or drawback of the suggested criteria is that one has to carry out several measurements using multiple frequencies, which costs extra time. Also, the other parameters, which other than the frequency, can be set using the same approach. Thank you.